Welcome back to Lecture 7 of Applied Machine Learning. In this lecture, we're going to look at a new topic called generative algorithms. In the previous few lectures, we looked at different kinds of supervised algorithms, and in particular, in the last lecture, we started to look at classification algorithms. In this lecture, we will introduce the general approach to defining machine learning algorithms that is called the generative approach. And a special case of this approach is going to be a set of new supervised learning algorithms for the kinds of classification problems that we have seen earlier. And in the first part of this video, of this lecture, in our first video, I would like to start by defining what it means for a model to be generative. So we're going to start with the concept of a generative model. Recall from our earlier definition of supervised machine learning, recall that applying supervised learning to a problem involves specifying a training data set which contains labeled examples, and then also specifying a learning algorithm. And when the learning algorithm is combined with the training set, we obtain a predictive supervised learning model. And this learning algorithm, we can think of it as having three distinct components: a model class, an objective which ranks the different models within the class of all the possible models by how well they fit the data, and an optimizer or an optimization algorithm that chooses the best model as defined by our objective. So in order to define a new set of learning algorithms, which are called generative algorithms, we are going to start by defining a particular model class that contains the set of generative models, and then we're going to discuss objectives and optimizers later. Now, recall also that in the previous few lectures, we talked about how we can define machine learning models from a probabilistic perspective, and we defined this particular kind of model, or this family of models, or essentially we started with the most general possible definition for a machine learning, for a probabilistic machine learning model, and this is how we defined it. So we said that a probabilistic model is a function that maps each set of x and y, each tuple of x and y to some kind of probability here. And here I'm assuming that this is a parametric probabilistic model, and the parameters of this model are specified by theta. And the idea of these models is that if our data comes from some kind of data distribution, then it makes sense also for our model to be a distribution, and then we can try to approximate these two models. And we saw that the principle of maximum likelihood is one way in which we can fit these kinds of probabilistic models. And also, even though here we're fitting a model over both x and y, we can still compute predictions out of this model by looking at the conditional distribution over y given x, and we can obtain this distribution from our full model by applying the following formula to this. This is just a simple identity from probability. So we define probabilistic models. And as I mentioned earlier, these models can be trained using maximum likelihood. It's a general approach that can be used to define a training objective for any probabilistic model. Here we're essentially choosing a set of parameters such that the model assigns high probability to data coming from the true distribution. And then we saw also a special case of probabilistic models, which were called conditional probabilistic models. and these are models that have this form. They are again mapping x and an x and a y to a probability, but now this is no longer the probability of seeing x and y. Now this is going to be the probability of seeing y given x. And these kinds of models can also be fit using maximum likelihood, except that the derivation is slightly different, but still the objective looks really similar. Here we are again choosing, we're trying to find a model that assigns high probability, high conditional probability to the targets given each x, where the targets and the x's are coming from our data distribution. And you should recall from the previous lecture that we saw one example of this approach, which was logistic regression. Logistic regression was one way of parameterizing a conditional model of this form, and the output of logistic regression was directly a probability between 0 and 1, and this was the probability of seeing a particular target y given x. So these conditional probabilistic models are we find them very often within different machine learning algorithms, and they're really important. So the distinction between these two kinds of models is actually really important, and it forms the basis of an important class of, two important sets of algorithms, which are called generative and discriminative. And the distinction between generative and discriminative it's a very important one in machine learning. We've seen a few of these different classes, or maybe different related classes along which, or different dimensions along which machine learning algorithms can be compared. We saw, for example, in the previous video, non-parametric versus parametric models. We've seen classification and regression algorithms. And now discriminative and generative is another important dimension along which we want to think about machine learning algorithms. So what is discriminative and what is generative? Essentially, this distinction is what I discussed earlier when I defined and when we reviewed the two kinds of probabilistic models that we have seen before. So the first distinction between discriminative and generative algorithms is the particular type of model that they fit. And we refer to these models also as either being generative or discriminative. And a generative model is a model that has this form, in which we fit a joint distribution over both the inputs x and the targets y. So this is our most general form of probability distribution that we have seen before. And it turns out this has a special name, and we're going to see why it's important to distinguish these two kinds of models later. But this full model is what is called a generative model. And the other kind of model that we have seen, the one that fits a conditional distribution, that one, we often call it a discriminative model. And again, here, an example of this was logistic regression. And we have actually not yet seen any real non-toy examples of generative models. We saw a little toy example that could fit in a table with 6 rows, but we haven't yet seen real examples of generative models, and we're going to see one in this lecture. So this distinction is one that I want to emphasize again, and I want to assign it this very specific name, these two very specific terms, generative and discriminative. So what is the difference between these two models? Why is it important? So the first and maybe really obvious distinction is that, well, these are two functions with the same signature over here, but they parameterize two really different kinds of probabilities. So on this side, we have a function that outputs a number between 0 and 1, and then when we sum this over x and y, the sum of all the probabilities has to equal 1. Here we have a different here the kind of function that we parameterize here is has really different properties. They now we only need for this probability to sum to 1 for every y. So here I'm just saying that the kinds of functions that we would use to specify these models would be different because these probabilities have really different properties. And that is the first point that I wanted to make here. Now, because these are different probabilities, they also involve different training objectives. And you have seen the example of conditional and general maximum likelihood. And these, when we apply them and we derive the objective, we typically get a different objective, which results in different predictions. So even though the generative model and the discriminative model can predict y from x, these predictions will tend to be different because we are applying a different objective to a model that's parameterized in a different way and has a different functional form. And as a result, because these two approaches are different, their uses are going to be different. And some of these will be some types of models will be more suitable to a certain use, and the other class will be more suitable to a different set of uses. For example, if we are interested only in prediction, we would use one class. If we're interested in generation or in other properties related to modeling X, then we would use the generative type of model. And I'm going to be talking more about the distinction between these two types of models and why specifically they are different and when we would want to use them in the following few lectures. So as an example that can make this distinction a little bit more concrete, let's look again at our data set of iris flowers that we have used in the previous lectures to demonstrate classification algorithms. So recall that in the iris flower data set, we have a collection of a few hundred data points where each data point corresponds to a flower. And for this flower, we have taken a number of measurements such as the petal length, the sepal length, and we have three types of flowers in this data set. Which are denoted by the different labels here, 0, 1, 2. And if we only consider the first two feature columns from the previous table, we can visualize this data set in 2 dimensions, which gives us the following scatter plot. Here, the 3 colors, blue, light brown, and dark brown, these correspond to 3 different types of flowers. And we see here that one type of flower clusters in this area, so these flowers are more similar they're more similar within their flower type than these two. So again, this is a 2-dimensional visualization of our data set. So an example of a discriminative model on this data set would be logistic or softmax regression that we have seen before. And another way of looking at what a discriminative model does is that it directly tries to partition the feature space into regions that are associated with each class. So here, for example, these blue flowers, they live in their own part of their feature space where they form a cluster. And the idea of partitioning the feature space is to identify that cluster, is to identify the region of the feature space where these blue flowers are located, and similarly find the region of the space where the other 2 kinds of flowers are. And these flowers will be separated by a decision boundary. So to put it in yet another way, given features X, a discriminative model will directly map to the predicted class. And this can be via a function such as this one, where this is a form of the sigmoid function with that takes in the score for that particular class. This is the form that's the logistic regression uses. But the high level point here is that we want to partition the feature space into different regions, and we have a function that at each point in the feature space, it directly outputs the class or the partition to which this subset of the region belongs to. This is an example of running softmax regression on our data set, and you can see here that we have partitioned the space into the following three regions denoted by the different colors. And if we invoke the softmax function, say at this point here or even at this point here, we're going to get the output blue. So at each point in this two-dimensional grid, we are directly specifying which class is the output. And now let's compare this to what a generative model would do. In a generative approach, we would instead do something that's a little bit different. So in the iris example, what a generative model would do is that it would first build a model of how each type of flower looks like. So in other words, if X is the vector of features that describes our flower, then we would try to estimate the following probability. So the probability of X, which is some vector of features, some vector of measurements, given a particular class. So for each class, we would learn a model of how this flower X looks like. Another way of thinking about this is that this is a model for how each flower is generated given a class, or it's a model over X which allows us to generate new flowers. And this is what gives this approach its name. So again, this is a different way of thinking about classification. It's a different way of thinking about classification that also leads to new algorithms, but they have a different philosophy. So again, step one is to specify this model of how each class looks like. And now, given a new flower, instead of trying to directly map to the class of this flower, we are instead going to match it against each of our three flower models. And then we're going to determine the model that fits this, or the model that looks most similar. This X prime will look most similar to one of the three models that we have found. And we're going to say that the label of X prime is the label of the flower model that matches it best. So if X prime looks like our model, looks like what is predicted as our model of iris setosa flowers, then we're going to say that the label is iris setosa. And mathematically, what this means is that we do the following operation. We are interested in knowing the most likely class under our model, and now we invert this expression using Bayes' rule. Again, in a discriminative approach, we would have this would be a model directly, but now we don't have a closed form. We don't have a function that measures this particular value. Instead, we have a model for each kind of for each type of class. So therefore, we apply Bayes' rule, and we obtain the following. Example here on the following formula here on the following expression that you see on the right. And now the maximum of the class, the most likely class, is given to us by the model that explains this X the best. So we will output the class such that the probability of X given Y is the highest under this class. In other words, we're going to compute the probability of this data point under each of our flower classes, and we're going to output the class that gives us the highest probability of seeing this point. So this is the general approach to generative modeling in the context of classification, and it's just a general philosophy for how to approach these problems. So given that we have these two approaches, generative and discriminative, which one is better? Which one do we want to use? We're going to be talking about this at several points during this lecture and also during the next lecture. But in brief, if we are only interested about prediction, well, we don't really need a model of X. So in other words, a discriminative model only models this distribution, whereas the generative model also is modeling X given Y. But we don't really need X given Y, so if we are only interested in prediction. And therefore, if we don't model it, then we would be solving the problem that we care about more precisely using fewer modeling assumptions. And in general, it will mean that the prediction in practice are more likely to be accurate. However, if we care about other tasks, such as generation or dealing missing values, or maybe we know the true model, we know that it's generative, maybe we can specify the process by which the data was generated and we can build a more accurate model if it's generative, then in these cases, we will want to use a generative approach. So again, these are two simple distinctions between the two models, and I'm going to talk about this in more detail later on. And for now, I will pause here, and then in the next video we are going to see our first example of a non-toy generative algorithm.